Hi, I'm Rob Jansen from the U.S. Naval Research Laboratory. Today I'm going to talk about our work, Once is Never Enough, Foundations for Sound Statistical Inference in Tor Network Experimentation. This is joint work with Justin Tracey and Ian Goldberg from the University of Waterloo. Our work is about Tor Experimentation. Tor is an anonymous communication system that separates identification from routing. Clients in Tor send their web requests through a series of 3 Tor relays. And as a result of this routing process, no single relay in the network can identify both the source of the traffic and the destination. So Tor provides unlinkable communication and protects user privacy and safety online. Now, because the traffic is sent through multiple Tor relays, it's generally slower to access websites in Tor than it is to access them directly. As a result, there's been a lot of research over the years on improving Tor performance. In order to evaluate how well these different proposals perform, we need methods and tools to help us safely conduct Tor experiments. A lot of these experiments can't be conducted on the live network for ethical reasons. We want experimentation results gathered using test networks to be accurate and dependable so that we can use them to make real-world decisions about the real network. So generally, when running Tor experiments, there are 3 steps. First, we need to model a Tor test network, and then we need to run the test network experiments and collect and analyze the results. We make contributions in all 3 of these areas in our paper. I'm not going to go over the details now, but I'm going to describe our contributions in each of these 3 areas in the following slides. And I'll start with talking about how we model Tor test networks. Okay, so our modeling approach uses data that's available and published by Tor Project. It's available on metrics.torproject.org. We use all the data that's available to make informed modeling decisions. One of the primary contributions in our modeling approach is to account for relay churn and the state of the network over time. This graph shows the number of relays that exist at the beginning of January 2019 as a solid line, and how many of those relays remain in the network over time. We see that 2,000 relays left the network by the end of January. And the dashed line shows how many new relays joined the network from the beginning of January through the end of January. We see that over 5,000 relays joined the network. So this shows that there's a very high level of churn in the network. And our modeling technique is to consider the state of the network over time in order to capture this diversity in relays that are coming in, joining and leaving the network. We sample relays from the full set of relays that we observe. We sample them according to their uptime during the modeling period and also according to their bandwidth consensus weight. A second area that we improve the Tor modeling process is that we simulate multiple users in each Tor client process to save RAM. The previous method was to simulate 1 user for every Tor client process, but that requires us to run more client processes, and we can, because these users are mostly idle, they're active and then idle for large periods of time, we can actually simulate multiple users in a single client to save resources. To run the Tor experiments in the test networks that we are modeling, we use Shadow. Shadow is a discrete event network simulator. It's the most popular tool for running Tor experiments. We conducted a performance audit of Shadow using the Linux perf tool. We found and fixed several performance bottlenecks in Shadow. We added a feature to shorten Tor bootstrapping time when running in Shadow, and we enabled other runtime optimizations. We also analyzed Shadow's networking and fixed some non-determinism bugs and also improved the network stack. Now, to showcase how our improvements affected the results, we compared a state-of-the-art experimentation approach from CCS 2018. This is table 2, which I shamelessly copied from our paper. We ran the same experiment that was run in previous work, and I'm showcasing 2 main results here. First, we were able to reduce the RAM usage for the same experiment run from previous work by 64% by making the improvements that we made. We were also able to reduce runtime by 94% by making the performance improvements. And as a result of these resource improvements, this allows us to support larger scale test networks than were previously possible. We are the first to run 100% Tor network with about 6,500 relays and about the traffic from about 800,000 users. We're the first to run this 100% network in simulation. And the third area is running experiments and then collecting the results and analyzing them. Okay, so running the experiments, when generating the networks that we run, the experiments that we run, this involves two levels of sampling. First, as previously mentioned, we sample a Tor test network using data that's available on Tor metrics at some scale less than 100%. Generally, this depends on the hardware resources available and the amount of RAM that Tor consumes. But we generally model it at a scale less than 100%. And that gives us a test network model that we can run. Second way of sampling is to run the same simulation multiple times using a different simulator seed. Previous work ignores these sampling choices and simply runs a single simulation for vanilla Tor and then a single simulation for each research variant. And they compare the empirical CDFs from each of these networks directly while ignoring sampling error. This is not statistically rigorous, and so we argue that one simulation is never enough to have statistically significant results. We need to do repeated sampling, not just of simulator seeds. We can't just run the same simulation multiple times with different seeds, but we also need to sample the Tor test networks themselves multiple times to have better diverse coverage of the diversity that's present in the live network. So we provide methods in our paper that help us quantify the sampling error by computing confidence intervals over the empirical CDFs that are captured from our experiments that we run. And our methods allow us to make statistical arguments for the results that we observe in our experiments, and it gives us more confidence in the conclusions that we draw from our results. So I'm going to give you an example of how this is done to sort of provide some intuition behind what we're doing. All the math and the results that just describe how this is done are in the paper. But essentially, suppose you run the same simulation 3 times, and this generates 3 empirical CDFs for a random variable. In this case, the example is the time to last byte, how long it takes to download a file. You get 3 empirical distributions. Our methods are to take these distributions and compute an estimated true CDF, which is shown by the solid line on the right graph, taking the mean over all y values on the left graph. At each y value, take the mean over the 3 available samples from these distributions. And then also, we compute the confidence intervals around the estimated CDF by incorporating sampling and measurement error. And the confidence intervals help guide us to understand how precise is our measurement, how much confidence should we place in the result that we've gathered. In the paper, we conduct a case study of Tor usage and performance to demonstrate how to apply these methods using a very simple example. So we use a simple hypothesis that increasing the amount of traffic load that the relays are forwarding in the network by 20% should decrease performance for existing clients. So we tested this hypothesis by running simulations in 100% loaded networks and 120% loaded networks, more congested networks, using different scale factors, a 1% network with 60 relays, 10% network with 600 relays, and a 30% network with 1,800 relays, approximately. And we run a different numbers of simulations for each of these setups, 420 simulations in total. We are particularly interested in how the network scale affects the conclusions we can draw from the results. So the results are shown here. For a 1% network, we can see there's 2 major takeaways here. This is showing the time to download the files. We can see, first of all, that the confidence intervals for the different load values are overlapping, significantly overlapping, for both running 10 simulations and for running n equals 100 simulations. In both cases, the confidence intervals are overlapping, which indicates that we don't have enough confidence precision in the results to make any conclusions about our hypothesis. In fact, we can see that the 120% loaded network, the orange shaded areas, appears to be to the left of the blue shaded areas, the 100%, which is the opposite effect of what we expect. We expect that adding load should make download time go up, not down. And so if we just use the 1% network and 100 simulations, we might come to the incorrect conclusion. So when we increase the scale to the 10% network with 600 relays, we see that these relays are better representative of the true Tor network. In this case, the confidence intervals are close with 5 with n equals 5 simulations, but there's still some overlap in the blue and orange shaded areas. But with n equals 10 simulations, these intervals start to separate. And with n equals 100, they're completely separate. And that gives us enough confidence to confidently say that indeed adding 20% load onto the network makes download times go up for the other clients in the network. And then at scale of 30%, we see, again, clearly the confidence intervals are clearly separate with either when running 5 or 10 simulations. So the overall general conclusion here is that more simulations are needed at smaller scales to get a specific CI precision, and fewer simulations are required at larger scales to reach the same CI precision. So the methods that we propose in our paper help us to conduct this type of analysis and helps guide researchers in better understanding the results and if they've run enough simulations or if they need to continue running more simulations to get a more precise result. So to summarize, the primary contributions are shown here, and our main results are shown here. We released all of our work. All of our improvements to Shadow have been merged into the public Shadow. We release artifacts for our research at the website linked below. So you can go there if you want to reproduce our results. My contact information is also shown. Thank you for your time.